All right, hello everyone. We still have a few people that are joining, but we thought we'd go ahead and get started. Thank you very much for joining us today to talk about learning all about PCB vias. My name is Lisa Holmes and I'm the Marketing Director at Royal Circuit Solutions. Before we begin, I just wanted to go over a few logistics. You should have a control panel on your screen. If you have any questions during the presentation, please use the chat box to answer them. We will try to answer the questions during the webinar, but we'll also have plenty of time for questions at the end. So now I'd like to go ahead and introduce our panelists. Our first panelist is John Lass. John is the Vice President of Engineering at Royal Circuit Solutions. He was actually the original founder of the company and has worked in the PCB industry for more than 20 years. John will be joined today by Matt Snogren and Mark Hughes. Matt is the head of process engineering at Royal Circuits, and Mark has been a design engineer for many years and most recently was the senior writer for All About Circuits. So now I'd like to go ahead and turn this over to John to get us started.
Thank you, Lisa.
And I'm on now, John.
Good morning, Matt.
Morning.
Again, thank you, Lisa, for the introduction, and welcome to everybody to our presentation on vias today. We can move on to the next slide. Thank you. So basically, we're going to talk about vias. We're going to go through kind of the basic concept of what vias are about, the different types of vias, the fabrication process and how some of these different vias are manufactured. Also how they're inspected to make sure that they meet the class 2 and class 3 requirements. And then some of the common design mistakes that we do see on occasion. And then of course we'll open up at the end for any questions. And then also during the webinar, if you want to type in any questions on the chat box, we can also address those at the time of the webinar if it makes sense. So again, we're talking about vias. We're going to be talking about the different pad sizes, the annular rings, anti-pads, non-functional pads, the plating wall, the SMT lands with vias in them, and then touch a little bit on teardropping to enhance the annular ring connection. So first of all, we'll talk about the basics of a via. A via is basically a connection to connect one layer to another. It can be all the way through the board. It can be just internally from one layer to another. It can be from an outer layer to an inner layer. It can be for routing traces from one layer to another, or it can be from connecting straight to a power or ground connection. But vias are very common in all multi-layer and double-sided boards. I don't know, Matt, if you want to touch on anything on a basic description of a via.
No, that was good.
Okay. Then we'll move on to basically just here's a picture of a via. You have a pad around the via that we'll be talking about later on, which is an annular ring. Depending on the style of the via, whether it's a micro via or a through-hole via, that annular ring can be smaller. And also you have what's called a anti-pad, which is the clearance around the via. In some cases, we have copper pour. It could be on an inner or an outer layer, and you want a distance away from that via pad to isolate it from any of the connections. Annular ring. So that's basically, and again, that could be on a via or a through-hole pad, but it's basically what's the area that's left between the drilled hole and the pad. So it's called an annular ring. Again, as I mentioned, depending on the style of via, that can be small or larger. Also depending on whether you're trying to meet class 2 or class 3 requirements, which we'll get into a little bit further on in the webinar, but that via can also have very, very small connection to one side or tangency. And that's basically what annular ring's about. Non-functional pads. So when we receive data in the CAM engineering department, 99% of the time we will remove the non-functional pads. Sometimes there will be a fabrication note specifying not to remove them, but it is good practice during the design process to keep the non-functional pads on the inner layers, so that when you're routing traces, you're keeping those DFM rules intact to keep the traces or copper pour away from the drilled hole, to make sure that you have enough clearances on an inner layer. Matt, I don't know if you want to touch base on non-functional pads at all.
Yeah, basically having them there forces you, if it's a 3 mil line and space design, it forces you to put the edge of the trace 3 mils away from the pad. And then if you have 5 mils of annular ring, that makes it 8 mils away from the edge of the hole. And that's a good distance to have good yields and reliable product.
I've got a quick question for the both of you. This is Mark speaking. What about non-functional pads on external layers?
Well, again, I'm going to chime in, and Matt, please come in behind me, but I don't think there's anything considered a non-functional pad on an outer layer, only because you have to have a pad for a connection. You can have a plated, barrelless, or not barrelless, padless barrel plated hole, but you still need to have some kind of pad, whether it's the same size of the drill hole or a little bit larger, but you have to have some kind of connection.
Yeah, it needs to be open during plating, so you get chemistry solution flowing through the hole, so you get even plating throughout the hole.
All right, so we'll move on to, I believe it's teardropping is next, yes. So it's common practice to do what's called a teardrop, and what that does is when you have a trace coming into a pad, we can add a teardrop connection that just basically builds up the connection on that side with the trace coming in, so that if you do have a very tight annular ring, or also what we call drill wander, which you'll see in some pictures later on, where the hole is typically not in the center of the pad as it's showing here. So if it's moving towards the trace with the teardrop, you have a much better connection. And that's kind of the purpose of a teardrop. Matt, I don't know if you have any comments on that.
Once we get to one of the other slides, if a hole breaks out of the pad where there is no trace, it's considered breakout. If that happens where there is a trace without teardrops, it's considered breakback. But if you give it a teardrop, it basically eliminates breakout at the location where a trace is connected to the pad when you have tangency.
I remember when we were speaking earlier that you gentlemen mentioned that not all engineers use teardrops, and I just kind of wanted to chime in. That might be because that their software, their electronic design automation software doesn't allow them to. Is that anything that can be added at the factory, or does that need to be done by the engineer so it's signed off by the engineer?
No, we can definitely add it in our CAM stage. Like I was mentioning before, that's somewhat of a common practice when you have really, really tight annular ring. So yes, we can. And then we have to run DFM rules afterwards to make sure that no violations were created. But it's definitely something we can do at the engineering CAM stage.
All right, thanks.
So land pads, or I'm going to just kind of focus on surface mount pads right now. A surface mount pad, you can have vias inside them. It's called a via in pad. It can be a blind via, or it could be a through hole via filled with epoxy. But that is, a very, very common practice nowadays with the very, very small land patterns or components that we're putting on boards. Also in the center of this quad pack, you can see that there's an area that is commonly filled with solid copper and then stitched with vias. and those can also be filled with epoxy and plated over, so that it's a little bit better for heat dissipation with that application. So the plated wall of a via, and as we get into the fabrication process a little bit later on, we'll talk more about that. But a via basically can be a half a hole, like a blind hole or a through hole. And during the plating process, we plate copper in through the hole, and that creates a barrel or a wall inside the hole. And that leads us into aspect ratio. So vias are typically smaller holes, for example, than component holes. And with that being said, you do deal sometimes with aspect ratio issues. Depending on the board thickness, you can have a very tight aspect ratio. We have pulse plating at Royal Circuits, and what that means is that we have up to a 16:1 aspect ratio, which helps on some of these thicker boards where they have to run smaller vias because of the tight routing. So that's one enhancement that we have internally. Matt, do you have anything to mention on aspect ratio?
Just that it's the, let's see, I had this prepared in my head a minute ago. It's the, Jesus, the diameter versus thickness. So if you have 10:1 would be a 6 mil diameter bit in a 60 mil thick panel. So if you go up to a 90 mil thick panel, the aspect ratio is higher. Not too many years ago, many people's limitations were 6:1, 8:1, maybe 10:1. Today, like John said, we can go up to 16:1. Doesn't happen very often, but from time to time.
All right, so we're going to get into the different types of vias, which we touched a little bit on earlier, but you have your through hole via, which is probably the most common. Again, it's just making a connection all the way through the board. It can be just making a connection from the top to bottom. It can be making a connection from a top to an inner layer, and then from another inner layer to another inner layer back to the bottom or top. You have blind vias, which starts from an outer layer and ends on one of the inner layers. It could be one layer deep. It could be multiple layers deep. You have buried vias, which are all on the internal layers. Again, can be just from one layer pair to another or multiple layer pairs. We have what's called a micro via. Our version of that is a laser drilled via. Again, that can be just on the outside down to one layer. That can be a buried stacked micro via where you have many of them on top of each other. And then what we're seeing a lot more of lately is back drilled vias. That's a through hole via that after manufactured all the way through the board, we come through and with vision drilling, we back drill, or it can be from the top or the back, but we basically drill out down to a certain inner layer, the barrel, the connectivity, which changes the signal integrity of that barrel or that signal. So this is just a description of the, or a picture I should say, of the type of vias. Okay, so the type of vias we were talking about. So you have through hole vias, you have stacked micro vias, you have staggered stacked micro vias. So one of the common practices that we're seeing is to do stacked micro vias where we do multiple lamination cycles. So you might start out with an inner layer pair from say 3 to 7, and we'll drill that and we'll plate it, and then they'll stagger off of those vias a land pattern, and then the next layer will be laser drilled down and then copper filled, and then again sequentially laminated, and then again another one, and that's called a staggered micro via. Matt, I don't know if you want to touch at all on that or any of the back drilling.
Yeah, if you have a buried via and then you're going to have a stack of laser vias above it, you want to stagger them a little bit from the buried via. So, and then some people think there's design or reliability issues with stacked laser vias. Therefore, if there's room, a lot of people are going with the staggered micro via. But the benefit of the micro vias is you can start with a smaller pad, which gives you room to route traces through your smaller or denser components.
And back drilling. Just from a designer's standpoint, I know we use back drilling on high-speed data lines just to prevent points of potential reflection. But maybe you guys could tell us a little bit about some of the difficulties you face when it comes to manufacturing boards with, I mean, how are back drilled boards made? What's the throughput? Do we have to throw out whole panels because of this, or does it increase our cost? What goes on once I order something with back drilling?
It certainly increases cost. The more depths there are in a design, the more time consuming it is, therefore the more it costs, and it might add a day or two to the cycle time. We've seen them up to 5 or 6 different depths in a design. Usually there's only 1 or 2, but sometimes there's a lot. And it can take, for a 10 panel lot, it can take a full shift to do, a multi-level back drill process on one machine. So it's tying up an operator, a machine for a relatively small number of panels for at least a full shift.
So I would be much better off if I was going to do some back drilling to make sure that I keep all of these signals on a single layer if possible then. So all my back drilling happens to a consistent depth. Is that what I'm hearing?
Yeah, the fewer depths required, the better.
All right, thank you.
And as it shows in the picture too, just a description of how we manufacture it. We actually build it as a through-hole via, just like a standard via, and go through the full fabrication process of the board. And then towards the very end, before electrical test, we'll go through a back drilling process as Matt described. And that's with a larger drill bit than what was used to drill and plate the hole, so that you can get the accurate amount of plating removed from the barrel.
And like John said earlier, it's called back drill, but back drills exist from the top side of the board and the bottom side of the board. And the intention is to remove that unnecessary stub of plating that goes down to the other side of the board, because it speeds up the signal. In this case, signal's going to go from layer 1 to 2, 3, 4 down to layer 5. If you don't back drill it, the signal actually goes to the bottom, comes back up, and then goes down the tray. So if you take that stub out, it takes less time for the signal to go down the trace.
Okay, well then I guess we'll move on to the fabrication process of how we build vias in a board. So there's a lamination process in all multi-layer boards. So the inner layers are what we call print and etched. So they're imaged. Everything that you want left on the copper is covered by dry film. And then we etch off the copper and then strip the dry film, and you end up with your circuit pattern. That's laminated in a press as shown here. And then after lamination, we go through a drilling process. So we have X-ray technology, which basically looks inside a multi-layer panel. Could be 4 layers, could be 22 layers, and lines up all of the fiducials on the inner layers and gives you a best fit drilling technology for good registration. and all the holes are drilled in the panel with the drill machine. And then after drilling, we go through what's called, we go through a direct metallization process at Royal Circuits. Some people or other fabricators use electroless copper. We use direct metallization, which is a palladium-based metallization. So after drilling, it goes through a deburr process and then a direct metallization. Then we go into an imaging step where we're actually imaging the outer layers on the top and the bottom.
That would be the equivalent of the middle picture with the blue.
Yes, with the dry
blue
foam
color is the photoresist.
Correct. Then we go through, after imaging, we go through a plating process. Again, depending on if it's a class 2 or class 3, we're plating copper in the hole. If it's a class 3, then there's more copper required in the hole, which also plates on the surface. And then after the plating process, we go through some stripping processes and then also some etching processes, and you end up with a via shown on the right-hand side. I don't know, Matt, if you want to touch anything there that I may have missed.
Nope.
Okay. That's just a picture of plating. As we mentioned, we have pulse plating at Royal Circuits. That's just kind of a shot of that. Vias and special processing with vias, as we discussed, there can be through-hole vias, and when they're through-hole, they can also be tented with LPI, which is on the left-hand side. And what that does is it tents the hole with LPI. It basically kind of prevents anything from getting into the hole. But there is always a chance when you tent a via that the tent can break because the thickness of LPI is pretty thin. The next process would be via plugging. What that means is we take LPI and we actually plug the hole, the full through hole with LPI. We then coat or tent on top of it. And that guarantees you 100% that you will not have anything going through that hole during the assembly process. And then I'm going to let Matt touch base on the V-in pad.
V-in pad is the example on the right. So we drill the holes, plate them, and we don't plate any circuitry at that time. We just plate through the barrel and a small pad on each side. We then fill the vias with epoxy resin, cure it, planarize it to smooth out the surfaces again, and then we'll go through the direct metallization process again to put palladium on top of the epoxy on both sides of the panel. And then we image it and plate copper across the top of the via. Via-in pad is often done either because of bore density. If you can put your vias in your pads, then you don't have to have vias where there aren't pads, so where there aren't functional pads. So it saves real estate. Some people want them there so they're closer to the component. In VGAs, on the dense ones, they have to be in pad due to space.
Can I ask, what's the benefit and what's the increased cost of calling out via plugging on my board?
Well, the benefit is that if you have, let's say you have some vias underneath a component that you're assembling, if you do not plug those vias, you have a chance of soldering, wicking up underneath it and possibly causing some shorts. If you tent it, there's a good chance that it'll prevent it, but a tent can break. So if you plug it with LPI, you have 100% plug via that will prevent solder from coming up. And it's a much more cost-effective way of plugging a standard through-hole via, than epoxy. Where epoxy comes in is if you have a via-in pad, so now you have an SMT pad, as Matt mentioned, that has to get plated over, so you can't plate over LPI, so you have to fill it with epoxy.
I've got another quick question for you. Why is it that whenever I order a board at some of the various board houses, that if I want any color other than green, like let's say I want to brand my boards all red, the price goes through the roof? Is there any particular reason, like if I go to a competitor to Royals, that they do that?
I don't know why the competitors charge extra. I can tell you that at Royal Circuits, we do not. We do many, many different colors all day long. I mean, green, as you mentioned, is fairly standard, but we do a lot of blue, red, matte black, a lot of white for LED reflection. We have one customer that requires purple LPI. So no, we actually do not charge extra for that. And us being in the prototype, fast-paced environment, we get a lot of color requests every day.
Thanks.
Yeah, being from other shops, I've seen the hassle with switching from color to color. Royal Circuits has just conformed and come up with a flexible process. But most shops, they've got their machine set up for green, and to change to another color, you have to clean the machine out, go through a lot of work to get a different color run. So that's why they charge more and really don't want to do it.
Okay, thank you.
So now we're going to get into inspecting a via. So after we plate the via, we need to inspect it to make sure that it meets the requirement of the design. Fairly standard are IPC 6012 Class 2 and Class 3. Class 2 is probably 95% of of what we build at Royal Circuits, basically because we do quick turn prototypes, and in the prototype environment, they're basically taking a design and just getting it proofed out. Depending on the application of the design, Class 2 is usually just fine. If they need Class 3, then after they proof out a design and getting ready to go to production, then they'll usually switch to Class 3. So I'm going to let Matt touch base a little bit on the breakout or tangency on vias.
Okay, the pad on the left basically has pretty much perfect registration. The pad in the middle, the internal layer pad has very good registration. The external pad, either the pad is misregistered from the hole or the hole's misregistered from the pad. But that one is maybe tangent, maybe it's a little broken out. And then the other one is certainly not broken out, the one to the right. Class 2 allows 90 degree breakout if your traces are teardrop. Class 3 requires 1 mil of annular ring, which is shown there on the right. Class 1 actually allows 180 degrees breakout and also requires a fillet or a teardrop.
And this is just a picture of some cross sections. So during the plating process, when we're done plating the vias, depending on the requirements, we'll cut out coupons that we have on the panels in all 4 corners, and we'll do cross sections to verify how much plating we have in the hole to make sure it meets the requirements before we move on to any further processing. I don't know if there's anything else you want to touch on cross sections.
On cross sections, we also verify dielectric thicknesses if they're specified in the design, copper thicknesses, registration. If the job has etch back, we measure that, verify that. Hole fill, we inspect the quality of the via fill. I think that's about it. Look for laminate issues, which is very rare, but we look to make sure it's not there.
And then also we can generate a report to ship at the boards on all those subjects that Matt just touched on cross sections, you know, if needed. So here's just kind of a picture of what we typically see on VIAs for registration. As Matt mentioned, different classifications allow some of these to be acceptable and some not to be acceptable. Picture number 2 kind of shows a VIA with a teardrop, so you can kind of get an idea of how, if the VIA is shifted that direction, you have a much better connection than you do in picture 1. And then picture 4 is showing complete breakout of a VIA. Somewhat typical of what you can see. So I guess now we're going to move on to some of the common design mistakes that we see come in. I'll touch on a few. One of them is overlap vias. So we see quite a few designs that come in where it's either buried or blind vias and they'll cross or overlap each other on internal layers. And that requires us to make some design modifications to the drill files, and in some cases create stacked vias to build or correct that design flaw. So that is, you know, one thing that we see quite often. Another one sometimes we'll see is in the design software, it allows you to, if you allow all layers to get micro vias, you know, added to them, or blind or buried vias. We've seen cases where on an 8-layer board, we have a drill file for every layer pair. So a 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8. That is certainly not recommended, and even if we were to build it that way, it would be extremely expensive and not reliable design. I don't know, Matt, if you want to touch on any other common design mistakes.
Just with the overlapping vias, if you have to have blind vias and they're not overlapping, it might be a 2 lamination job or a 3 lamination job. But if they have to overlap and you go get into stacked micro vias, it can turn into a 5, 6, 7 lamp job, which is going to take a lot more time and a lot more money.
I'd like to jump in on the insufficient AnyPad images. So on the left, we've got a green and a kind of salmon-colored picture where it looks like there were some non-functional pads that the designer removed. And on the left, it kind of looks like there may be enough space to get away with that. But over on the right, in this grounded grid area, you've got those 4 non-functional pads that have been removed and the vias poking through. I mean, how much do these drills drift? How dangerous did this designer get to creating a non-functional board?
6 mil vias, it's not uncommon for there to be a couple thousandths of wander in any direction on the bottom side of the panel as opposed to the top. They, you know, the top side, they're registered when they go in, but it's such a flexible bit as it goes through the panel. We call it wanders a little bit. So coming out the bottom, there's random misregistration. And on your lower layers, you can have issues. And then your registration isn't going to be perfect to begin with, layer to layer and drill to layer. So when all these things add up, it's best to have edge of drill to edge of internal metal feature of 8 mils if possible. It's not always possible, but when it is, that's a good place to be.
Now, would those errors always show up on the electrical connectivity tests? I mean, I know Royal does electrical connectivity on every board they sell, but could this cause a latent problem?
Yes, if a design has less less clearance than that, then there can be latent defects.
Thanks.
So some of the less common design mistakes, but we do see on occasion, is just clearance violations. So if your DFM rules are set up correctly, or your DRC rules in your design software, then routing, it will come out correct. Sometimes if there's what we call a same net violation, and the design system allows you to ignore the same net, so you can basically create a 1 mil air gap on a same net. We still don't recommend that, even though if it shorts out, it doesn't cause a problem. It's the same net. But from a manufacturing standpoint, if we get really, really tight features, we can have different problems in manufacturing, such as dry film peeling and overlapping, and then causing opens later on in the process. So we do recommend that you treat all same net air gaps the same as individual nuts.
So what do you think happened on this board?
I guess it was probably designed with less than 3 mil space. Not entirely sure, but.
Is that something that if the designers had done a DFM check through the PCB manufacturer, that would have been caught? Would Royal have caught this?
Yeah, definitely that would be, if they're different nets, this definitely would be an issue. If it was down to 1 mil, we would have to reject it. So we would send a hold question or an EQ question and let them know that there is a 1 mil violation, and that would not be manufacturable as is. Again, if it's the same net, we can make it work, but it's still not recommended because it can cause problems later on. But we definitely would catch individual nets from a DFM standpoint.
Thank you.
And I suppose on that subject, Lisa, we could do a full webinar on just DFM.
Well, how many, I think one of your employees told me that something like north of 90% of designs get put on hold for DFM issues?
Yeah, for one reason or another, absolutely. There are, many issues that arise when we get the data in. So that's definitely room for improvement there. That's why I said we could do a full webinar on that to try to help designers clean up their designs before they submit them.
I know I'd be interested in that.
So now I guess we'll open up the panel to any questions. I saw one on LPI that Mark already answered, but any other questions were
well, let's share that with everybody. Let's share that with everyone in case they didn't see it. The question was, are there any disadvantages to using different colors for the solder mask?
And the answer was no. I mean, to my knowledge, the only one that comes up at all on occasion, and it's really more for rework, is if you use black LPI, it's harder to see anything underneath it. But as far as one LPI to another, it's just pretty much a color change. It's all the same materials.
Oh, looks like we've got another couple questions in. Oh, Jerry says, I'd be interested in a webinar like that also, I believe referring to DFMs. And then Howard says, we use one color for prototypes and another for released boards. We have not seen any initial charge. I think this is just a comment, but he says, finishes with, perhaps this could be the case for a very high volume shop, but our company buys no more than a few hundred boards at the time. Thanks, Howard. So yeah, you can definitely do that with Royal. If you've got multiple versions using multiple colors, certainly make sure that you're not testing the wrong board. Something that I've been guilty of before. You've got 3 or 4 revisions out and you confuse 2 and 3. It happens. What other questions? Sorry, go ahead.
I was going to make a comment on that. That is a common practice that we do see, that they'll use one color for their R&D boards, and when they go into production, they'll change color. So that is a very common practice that we also see here.
what other questions do people have? Well, let me ask then, what brought everybody to a webinar on vias on this wonderful Tuesday morning / afternoon? Is it simply the fact that your employer pays you to watch webinars? I'd be okay with that. They're not going to tell.
It doesn't look like, yeah.
Oh, we've got Howard. Thank you, Howard, for saying he wants to learn the latest technology. Were we able to provide something useful? Oh, good. And then in the chat box, we've got Debbie asking, what are the design constraints we need to follow when designing metal edge PCBs?
Matt, do you want to touch base on the metal edge PCBs?
Not really.
I'm trying to understand what I mean by metal edge. If you're just talking
probably
about
edge plate.
Yeah. From a routing standpoint, you know, you want to try to stay at least 15 mils away from the edge on inner layers, and a minimum of 10 on outer layers. I'm not sure if that's what they're referring to.
Yeah, so if you want the inner layer to not be electrically connected to the edge plate, you want a 15 mil clearance. We need room for tabs. So if you want, you can't have 100% edge plate. So at a minimum, you would have to have some tabs to hold the board in the panel during fabrication. And the bigger the board, the more tabs we need.
Does that answer your question, Debbie? Maybe I could ask, what are some just common rules of thumb? If I'm going to go design a board for prototyping, I know what your minimums are, but if I want a board that I want it to work if possible, right? I know I can get down to a 6 mil drill if I need to, but what's your usual minimum recommended rule of thumb via size for typical components? I mean, not talking about BGAs and all that, but if I'm doing some ground returns for something or whatever it is.
You can come back in an hour. Sorry, I got interrupted.
So I'm going to let Matt touch base on that just because I know that there's we have different requirements for vias. He mentioned at one point, you know, with a laser via, we can have much tight annular ring because the registration is better. With a mechanical via, you need a much larger pad. And then based on the class requirement, again, you would even need a much larger pad on a class 3 to ensure that you have enough annular ring left over.
Matt, did you want to add anything?
I got interrupted for a moment. I'm in a hotel room and the person came to clean the room. So
I heard, and you sent her away. Just want a messy room. I understand. So the question really was, can you offer any rules of thumb for designers that, okay, we heard what your minimums are, but minimums usually aren't best practice. So what's your general, you know, what would be your preferred via
well,
size?
for 062 and thinner, we do 6 mil vias all day long. So that's not a bad via size. Preferably give us 16 mil pads. And then if you've got BGAs, what did we say yesterday? Less than, what was the pitch, John?
We had 25 mil 0.6 millimeter, 19 mil 0.48, 17 mil 0.44.
Yeah, basically, if you need your pads to be smaller than 16 or 14, you know, we could probably push to, in order to get a 3 mil line in space between the pads, then we really need to try to go with laser vias. Laser vias can be drilled at 6, 5, even 4 if the dielectric thickness is thin enough. And the nice thing about laser vias is they only need 2 mils of annular ring in the design. So if you drill it at 6, you only have to have a 10 mil pad, as opposed to a 16 mil pad. And laser vias, if you can get all your tight routing done on layer 1 and 2, for instance, then we can have laser vias from 1 to 2 and still be in a single lamination job, so it doesn't add, you know, too much cost. If you need to have the dense routing down on layer 3, then we would have to do a sequential lam, so we'd have to have laser vias from 2 to 3 as well as 1 to 2. So yeah, that's it.
All right, we've also got Henry Hu. Can you talk about design guidelines for blind vias for EMC?
I can't.
I'm not sure what they mean by EMC, Mark.
Yeah, I'm not immediately sure either. I'm doing a quick Google search. But Henry, if you want to jump in and maybe spell out that initialism for us, that would be great. And while we're waiting for Henry, we've got an anonymous attendee. What are the main registration problems you see that are common for boards?
Sure. So registration, believe it or not, has gotten a lot better over the years, just with the improvements on equipment and drilling capability. But if I wanted to pick one that's most common is when we get unbalanced constructions. That can happen in 2 ways. One is if we have a controlled dielectric stack up where there's multiple different thicknesses that are not symmetrical. Then during the lamination process, if we have, for example, a 3 core in one opening and a 10 core in another opening, we have predetermined scale figures that we use or numbers that we use to try to predict their movement. But when you have different core sizes, it's much harder to predict. So that's one area. Another area is if we're doing multiple laminations for blind vias, and again, it's not symmetrical, then you're trying to laminate 2 unbalanced packages back together that have a harder time lining up. One example would be if you're doing a 1 to 4 and a 5 to 8, both blind vias in those 2 packages and bringing them together for final lamination, those line up pretty well. If you had a 1 to 2 and then a 3 to 8, then that's much more challenging. So those are just some examples that we see. But in general, if you keep your stack up balanced, registration is pretty solid nowadays.
All right, Henry jumped in and it suddenly dawned on me what he was talking about. I'm sorry, Henry, I've got it now. Google, you were useless. So Henry followed up and he said, for example, I need vias for EMC along a trace, so electromagnetic control. What's the best practice for distance between these vias? So what he's asking is if you're doing via stitching or building a little wall to isolate the electromagnetic energy along a trace, and he's talking about blind vias. So presumably we would have ground on top and bottom layers, and then we would be making a wall on either side of the trace. So what size via, what spacing?
Well, typically, we actually see a lot of stitch vias in the RF designs, and it's usually between layer 1 and 2. And again, depending on the dielectric spacing of 1 to 2, when we're doing a blind via, the aspect ratio needs to be 1 to 1 maximum, preferably 0.8 to 1, but 1 to 1. So if you had a 10 mil dielectric from 1 to 2, then you'd be using a 10 mil via. I'm gonna let you touch base on the gap between the 2, but I think you would want at least an 8 to 10 mil gap between the pads. So depending on the annular ring on the hole, that could be up to 15. Oh, we may have lost Matt.
Lisa might have muted him because of the siren in the background.
Sure. Well, in any case, so that I guess what I'm trying to get at, one of the driving factors is the dielectric spacing. So if you have, you know, an 8 mil dielectric spacing, then your view needs to be maximum 8 mils, 10 mils preferred. And you know, you would use your same design guidelines as far as the spacing in between. You know, if you can hold a 5 mil air gap between pad to pad, then that would be fine.
All right, we've got Guy Clark. Are there special considerations for vias in heavy copper pads like 2, 3, 4 ounce copper?
Heavy copper, I'm sorry, so are there special considerations for heavy copper pads like 1, 2, 3, 4 ounce copper? Well, in general, any heavy copper designs, you want large traces on large pads and big air gaps. That'll be one thing on DFM we can talk about when we do a DFM webinar, but we get a lot of 2, 3 ounce, 4 ounce designs, and they do not give us enough air gap to manufacture it. So I think that would kind of be hand in hand on the pads. You'd want to make sure that they're, you know, larger and the air gaps are much bigger.
As far as via size in heavy copper, those designs tend to have larger holes. Honestly, we've never had one come in with small enough vias to cause us a problem, but I could see, you know, if we were trying to drill 6 mil vias, we might start having trouble, but it's just never happened because I don't think they ever have those small holes.
Is there any reason in my layer stack up that I would want the heavy copper on the outside of the board instead of on the inside? Maybe we could tell people how boards are made quickly.
Again, as long as you follow the right design guidelines for the air gaps, inner layers are typically easier to manufacture with the heavier copper. Outer layers is a plating process, so that always adds another factor to it. You know, but in general, I'd say inner layers are probably a little bit easier on the heavier copper.
All right, we've got new questions coming in from Anselmo. Before you fabricate a board, do you guys have the capability of identifying issues that could result in PCB warpage? If that's the case, would you provide some recommendations to the designer to prevent it?
Yes, so at the planning stage of manufacturing a board, we review the stack up. Any unsymmetrical or unbalanced stack up always has potential for warpage, and we do advise the end customer that there is a chance to give them, you know, the time to review it and maybe change it, and we can give them a recommendation if they ask for it.
Okay, by unbalanced stack up, you're referring to having, if you were to cut a board along the middle of the, you know, create a mid plane and slice it and open it up like a book, you want equivalent weights of copper on each layer, right? So if we're a 4-layer board, layer 1 and 4 are heavy and power planes, and layer 2 and 4 are signal planes. That would be okay, but we wouldn't want layer 1 to be power, layer 2 to be signal, layer 3 to be power, layer 4 to be signal, something like that, right?
Not so much that. You can mix copper weights, you know, relatively on an inner layer. I mean, you know, if you have a 1/2 ounce on one side and a 4 ounce on another, maybe that's not recommended, but it's more the dielectric spacings is what I'm referring to. So that you want to have a symmetrical dielectric spacing. For example, on a 6-layer board, you'd want to make sure that your openings between 1 and 2 and 5 and 6 are identical, and then 2 and 3 and 4 and 5 are identical, and then the one in the middle doesn't really have to be, well, it's by itself, so I guess by default it's not symmetrical, but the other ones, as long as you keep them symmetrical, you'd have a balanced stack up. If you had a pretty extreme difference between your dielectric spacing between 2 and 3 and 4 and 5, then that's what I'm talking about, and you can definitely get warpage in that situation.
And when does the board warp? Is that during manufacture or during assembly?
It is during the lamination process. Matt, do you want to touch base on that?
Yeah, during the multi-layer lamination process, the different thicknesses of material grow and shrink at different rates. So if you've got a thicker core on one side of the panel than the other, then during the lamination cycle, that thin core is going to actually grow more. And then the resin all sets up and hardens. And then when it cools down, that thin core is going to shrink more. Therefore, we're going to have warpage toward the thinner core. Also, if you had blind vias, say, from 1 to 7 on an 8-layer board, you know, we have to build the 1 to 7 sub first, and then we add layer 8. If we're going to add layer to one side, it's going to warp.
All right, thank you. And our last question, because our guys have to get back. I just see that note from Lisa now. My apologies for that. But we've got one last question from Tom, and his is a correction to his previous question. Why is it recommended to specify the via hole tolerance to be +0 minus hole diameter? I.e., if a via has a 10 mil hole, the tolerance is +0 minus 10 mil. Why is that recommended? And what do you do when the via hole tolerance is specified this way?
So I'm going to let Matt answer that one.
I was going to let you answer it.
Oh. Well, I can tell you from okay, I'll start it out, Matt. You can finish it. Basically, a via, when we go through the DFM process in CAM, if we start running into DFM violations such as clearances on inner layers to copper, now we want to start reducing that via as long as we don't violate the aspect ratio to make it more manufacturable. So therefore, you know, if we had a 10 mil via and we were going to finish at 10, depending on the final finish, we'd have to drill that hole 3 to 4 mils larger before plating, and then would finish at 10. So now you're creating a tighter clearance. So if we drilled it at 10 or possibly 8, now you might be finishing closer to 5 or 6. And that's why we have the tolerance of minus the hole size.
All right,
Yeah,
gentlemen.
so it gives us room to give ourselves more starting annular ring. Also, vias sometimes will plug with solder mask, and there's no way to avoid that. So if you have a ±3, then technically a plug via is not acceptable, but it needs to be on certain diameters.
All right. With that, I think we've answered all our questions. Lisa, if you're still around, I think we're ready to close this out.
Yeah, I am. I just wanted to thank everybody for participating and being here with us today. We'll be emailing you a recording of today's presentation along with contact information for John and Mark and Matt. So please feel free to reach out to them with any further questions. And thanks again for joining us, and we'll let you know next time we have our next webinar, which sounds like the topic will be around DFM. Thanks, everyone.
Thank you.